This is section 3.1.3 and this is Laplace equation in two dimensions. So I can come here and write from here these two. So this is curly square over curly x square and v plus curly square over curly y square and v is equal to 0. Now as usual we say that when we are having a second order differential equation, then it is having two constants involved. But it is not like this, because when I look at this one, it was a one-dimensional equation here, means and two constants were involved in the solution. It was a second order differential equation, and then it will have two constants, and here in the solution we are having two constants involved. That is okay. But when I come here, it's again a second order differential equation, but we will have to keep in mind that this is a second order partial differential equation. So the number of constants will be, just look at that one. When I was considering one dimension, the Laplace equation in one dimension, then it was having two constants there. This one, so its solution is not that simple that we say that it's a second order differential equation and there will be two constants involved. It is basically a second order partial differential equation, and we will have to solve this one. So to solve this one, let's say we are having to imagine this thing, the solution of that one dimension, it was a straight line, and the solution of the two dimension, because now our v is basically a function of x and y. So its solution will be a sheet. It will be a surface and not a straight line. And now that surface will have no extreme values. If the extreme values will be, they will be on the endpoints. But for this one, for the one dimension, we were very relaxed to have the endpoints in a straight line. But here the things are a bit complex. That those endpoints we cannot say in a surface that which are the endpoints. So it's a function of v xy. And it will also be an average of a point in a given area. So it's, for example, we consider a point here and then consider a circle around it. So circle is basically a surface. Now the average value of this will be basically this point. Is the average value here, when we were having this one, these are the endpoints, and here is the average value at the midpoint. Now here when I consider a surface, then what will be the average value? So if you consider any other in one dimension, any other points, then the average value will come like this, and this will have that any circle, it will concentrate toward the center is the average value. So we will have v of xy equals 1 over 2 pi r, and around a circle, this is basically the circumference of this circle. This is value, the radius value is r. So we are having around the circle and v dl, or potential, and along this one, along DL, what this will give us? This will give us the DL around a closed circle will give us the circumference of this circle, and our V will come out to be the average value of this system. So it's a kind of, you can say, the a kind of like this, that if I'm having the V along this axis, and this is basically V of xy, and here is y and here is x. Now on this plane, if I consider on this plane, this is a plane xy plane, and let's say I consider a circle. Now on this plane is a flat surface, so the circle and its average value here. But what about the solution of this differential equation? The solution of this differential equation will be a sheet like, so it will not be a flat sheet. Consider it a wavy like this one here. It's very difficult to plot such thing here with on a board. It's very difficult to plot such things on boards. Okay, so it's a kind of that you cut. Let's say we are having a mold, or let's say a piece of wood, and we cut it wavy like, and then on that wavy like we just put a rubber, we stretch a rubber and fit on that one. Now here consider that if, for example, we are having a wood, for example, it is empty like just a hollow pipe like, and we stretch a rubber on it, it will become a drum. So it's a flat surface on a drum then. And when we have let's say we cut a wood, and the wood like in a wavy shape, and now we fit on that one a rubber, we stretch a rubber over it. Considering any point here of radius r here, then what the values here on this one? So this is flat surface, and here it is a kind of wavy, not a flat surface. So it will give the average value just like on a flat surface. The other thing is that this sheet, this two-dimensional sheet or surface will have no local maxima or minima involved. If, for example, it's like this one, if I put a ball here, and this ball will roll down and will get off this surface. So it will be rolling, but it will not find any pocket or dip there, so that the ball stay over there, the ball stops over there. So it's a kind like the slope there. The slope can be negative, can be positive, can be zero, but there was no local maxima or minima there. Similarly, on the sheet we will have no local maxima or minima. And this is one thing that you can check the comment in the Griffith's book, the method of relaxation, or the method which second order differential equations are being solved, or harmonic equations are being solved, that we take average, we take points and then the average of it, and then we go closer to that one and we find the solution at some point, and then further getting closer, and then the solution is not varying at all, and we on computer solution we say that this is basically now the solution of the second order differential equation, which we call the method of relaxation. So this is the Laplace equation in 2 dimension, and then we will, after this one, we will discuss the Laplace equation in 3 dimensions. Now, it is very hard to interpret Laplace equation in 3 dimensions because now it is very hard to visualize this thing, that how it will be in 3 dimensions, because in 1 dimension the straight line was very clear. Then in 2 dimension we can imagine a sheet, but when we are having a 3 dimension, means volume, then what will be the local maxima or minima? This is something which is very difficult to understand there, because if, for example, I consider a volume and then there is a dip in that volume, then basically this dip is on the surface of it, like a hollow sphere, and a dip there, it is having some depression there, then the depression is basically on the surface. So on the volume it is hard to imagine, so we will consider its solution and we'll discuss it in section 3.14. and 3.14 is here 3.14, and this is Laplace equation in 3 dimension. Laplace equation in now in the Laplace equation in 3 dimensions, we will consider all the 3 dimensions, and we will here prove this thing that whatever we said earlier is right. And now in the 3 dimensions we will not be able to say things like the 1 dimension, because, let me repeat, in 1 dimension we say that Laplace equation is giving the average value and there is no local maxima or minima, and the maximum values are at the endpoints. So if the maximum value is at the endpoints, then average value will come exactly at the center. If there would be a possibility that the maximum, any local maximum or minimum does exist, so the average value will shift from the center toward the maximum or away from the minimum. So that's the reason that extreme values are on the end points. When we come to the 2-dimensional situation, in 2-dimensional situation, we said that the value at R, at the center of a circle, is basically the average value at R. Now whatever point I take on R, then the center point is coming out to be the circle. So this thing is average over a circle, and we are getting again the average value of the Laplace equation or of the potential. There is no local maxima or minima over here. Thus, if we put a ball here, then it will roll down. But this doesn't mean it is going to a local maximum, local minimum. Basically, this is going down and it will go up. Local minimum means that it will have a dip, a pocket somewhere that the ball will go and stop over there. So it is not possible here, and it is against the average value serve. Here, when we say that V is being the average value on this surface, so it means that the maxima or the extreme values are basically on the boundaries. Now we will extend this situation towards the 3 dimension. In 3 dimension, we will replace the circle with a sphere. So we will write that V as a function of R is basically, here this will come out to be closed surface integral and it is on a spherical surface. So it is spherical surface, and it is on a sphere. So here this will be V and now it will be dA here, because this is dl on a 2 dimensions, so dA will become on 3 dimensions, and as this is the average value, so it will be divided by the A's here, dl integrated on a circle, and it gives you the circumference. So here dA integrated on a sphere, it will give us the area of the sphere, so 4 pi and r squared. Here is we will consider a sphere of radius r, capital R, so this will come out to be 1 over 4 pi, and that spherical radius r square and integral on a closed surface, and this is a sphere and V dA here. Now when we consider such a situation, then what does it mean? The average value will be at the center of the sphere, while extreme values will exist on the boundaries wherever we will consider, so it will be on the boundaries. There will be no local maxima or minima, means there will be no dip in the surface. So when there will be no dip in the surface, we are actually just complying whatever we said in 1 dimension, whatever we said in the 2 dimension, and now we will prove this thing in 3 dimensions as well.